This is sine of x. This is sine of x over x. By the end of this video, I'm going to blow your goddamn mind, and you're going to fall in love with this function, the most beautiful function in mathematics. I guarantee it or your money back. Now let's get started. What is the sine of 1? Well, if your answer is some random crazy irrational number, then well done, you're right. This number has nothing to do with pi, it has nothing to do with e, it's just some meaningless crazy number. Now, what's the sine of 2? Well, if your answer is some random crazy irrational number that has nothing to do with pi and nothing to do with e, then well done, you're right again. Now, if you're feeling like a genius, let me hit you with a curveball. What is the sine of 1 plus the sine of 2? Well, actually, it's pi over 2. Nah, I'm just kidding. It equals some random irrational number that has nothing to do with pi and nothing to do with e. And this should absolutely be the case. The pi goes inside the sine function. It has absolutely nothing to do with the numbers that come out. Sine of pi over 2 gives you something decent. Sine of pi over 10 gives you something decent. But 1 radian is some irrational, meaningless number of degrees. So of course you're going to get garbage when you take the sine of it. It's like trying to plug some Fahrenheit temperature into Newton's second law. The units literally make no sense, and you'll only get garbage. Now, at the risk of you leaving this video, let me beat this dead horse even more. The sine of 1 gives you garbage. Add on the sine of 2 over 2, you get garbage. Add on the sine of 3 over 3, you get garbage. And if you keep adding them up, you get pi minus 1 over 2. Now hopefully your mind is blown at how ridiculous this is. It's like if I added my height and my weight and out pops my credit card number. There's literally no reason this should be the case. But fasten your seatbelts and say goodbye to your sanity, because we've only dipped our toe in the rabbit hole. Now hopefully it's clear to see that the function coming into play for all this wackiness is sine of x over x. In fact, this function is so important, so near and dear to our hearts that it's given a name. Sinc of x. By the way, in high school you might have heard about things like cosecant and cotangent. No, those are useless, and no engineer will ever talk about them. But Sinc is insanely useful, and absolutely worth having its own name. Now one quick point I want to make is, you should notice that at x equals 0, you get 0 divided by 0, which is indeterminate. But the limit as x approaches 0 exists, and is 1. So just for simplicity, as a matter of convention, we're going to ignore the discontinuity and define the function to be 1 at that point. Now, hold on, because we're jumping into hyperspace. I told you that if you sum Sinc for the positive integers, you get pi minus 1 over 2. Well, what happens if you sum over all the integers? Well, in that case, you literally just get pi. Absolutely beautiful and absolutely bonkers. But wait, we can get crazier. What if I completely changed the function and squared each of the terms, just for the hell of it? Now a sum that made no sense before makes even less sense. So what do we get? We literally get pi again. I literally squared every single term and got the same damn answer. At this point, I hope you're starting to think this video is an April Fool's joke. Maybe you'll wake up back in Kansas and this was all a dream. But I'm sorry, Dorothy. This is cold hard mathematics, and it's more real than Kansas will ever be. Alright, since I'm acting sus as all hell, let me just replace the sum with an integral. Instead of just the integers, now we're integrating over all the reals. What will I get? If for some reason you're crazy enough to guess pi, then you're absolutely right. Literally, replace the sum with the integral, and nothing changes. At this point, the math police are about to break down my door. But I'm still not going to stop. Now again, what if I change the function completely by squaring it? What should the integral give me? Yes, that's right, you literally get pi again. Now at this point, pi is gonna haunt your nightmares. But oh no, the beautiful Sinc function still has so much more to give. The rabbit hole isn't gonna stop. Back to sums again. What if instead of doing the regular sum, I did the alternating sum, where I switch between adding and subtracting the terms? Well, first off, I hope you're not blindly guessing pi, because changing some of the terms to negative has to change the sum. So, what do we get when we add and subtract all this irrational garbage? If you guessed 1/2, the nicest fraction there is, then you are out of your mind, but you'd also be right. I hope you understand how this makes absolutely no sense. It's like adding e and pi and ending up with a nice whole number. It's like adding my credit card number and my social security number and somehow getting my blood pressure. But you know the drill. What if I'm a maniac and just square everything? Yep, I get 1/2 again. At this point, I hope you've given up on your sanity, because now I'm gonna cube everything. That's right, you might have heard of sine squared, but now I'm literally just going for sine cubed. So what could I possibly get? Yep, I get 1/2 yet again. Math is literally broken and nothing makes sense anymore. Call your therapist and tell him he's a rich man, because you're never gonna mentally recover from this. At this point, I hope you're thinking two things about the Sinc function. Oh my god, I'm in love. This is the most beautiful function in math ever. And also, what in the hell is happening? How on God's good earth is any of this possible? Is there a glitch in the matrix or something? Well, the reason has to do with why the Sinc function is so insanely useful to engineers, and in signal processing in particular. You see, the Sinc function is an irrational mess. But if you look at its frequency content, that's where the magic happens. In particular, if you take Sinc, hit it with a cosine wave that has some frequency omega, and integrate out the result, what you get is how much the frequency omega resonates with the Sinc function. This is also called the Fourier transform of the Sinc function. What's amazing is that this Fourier transform has the most magically simple form. It's equal to a constant pi between -1 and 1, otherwise it's always 0. This function could not be nicer, which is why Sinc behaves so amazingly. All of the crazy sums and integrals and squaring I told you we were doing have corresponding operations that can be performed in the frequency domain. But because the function in the frequency domain behaves so nicely and so simply, all of the answers end up being highly elegant and nice. As a side note, this is also why Sinc is an insanely useful function in signal processing. When you want to perfectly filter out certain frequencies, either for a radio transmission or editing a song, the Sinc function provides the key theoretical tool to do that. Now hopefully this answer satisfies you, but honestly I still haven't explained why the Sinc function should look so nice in the frequency domain. So for the motivated of you, I'll provide some links in the description. Definitely consider checking out the Wikipedia articles for the Sinc function as well as the Dirichlet integral, which show you the dirty math involved in calculating these things. Anyways, thanks for sticking around. This video was motivated by 3 Blue 1 Brown's Summer of Math Explosion contest. Consider checking out some of the other entries, or making your own math video. Now, if you'll excuse me, I have to go back to procrastinating on my PhD thesis.